This is Unit 7, Video 3. In this video, we will talk about the heating curve and some calculations involved with the heating curve. Now, the heating curve is a graph, a type of graph that shows a substance going through the three phases of matter, from a solid to a liquid to a gas. And there are five distinct portions to the heating curve. Now, this is like a stylized, a perfect heating curve. In reality, the heating curve isn't as clean cut. You'll actually see it be a little more curvy. In reality, it may kind of look like this, being a little more curvy. But for the sake of clarity, we'll just kind of keep it nice and straight, nice and crisp with the edges. Now, what happens is you always begin with a solid down at the bottom. So this is the solid at a certain temperature. Realize that solids can actually attain a very, very low temperature, any way down, all the way down to absolute zero. So as cold as you can get it down to absolute zero. And then as you heat up a solid, now temperature on the heating curve is on the y-axis. So here's temperature, usually in Celsius, but it could be in Kelvin or Fahrenheit. And then on the x-axis is time, and sometimes they put energy. So it can either be time or energy. Energy is actually most commonly seen. You'll see the official one that I'll show you will have energy down here. And so as you heat up the solid, the temperature, notice, goes up. So as the temperature goes up, eventually you get to a point where you encounter a flat line. Now, this flat line corresponds to melting. The solid is actually being melted. So notice we are adding energy, or time is passing as we go this way, but the temperature is not going up. And this is a very important characteristic of the heating curve. The temperature is staying steady. The reason for that is because during melting, energy is going into breaking the bonds between solid particles, the intermolecular forces. So breaking the intermolecular forces at this point. And it takes an amount of energy to do this, and that energy can actually be calculated, how much energy it takes to do this, but the temperature stays the same. So this would correspond to the melting point of the substance. So say the melting point of the substance is 14 or something degrees Celsius. So again, this is the melting point. So if you want to, this is the melting point. So all throughout the time the substance is melting, the temperature is not going up. This is important to understand. Then once we've finished with melting, you start heating up the liquid. So this portion right here represents the liquid. And as we heat up the liquid, the temperature, notice, keeps going up. That makes sense. Then we get to a point again where there's a flat line. And this flat line represents now boiling or vaporization. The same thing happens during vaporization. The temperature stays constant. So if we say that the boiling point is maybe 200 or something degrees Celsius, this again is the boiling point of the substance. And in this case, the heat is actually going into breaking intermolecular forces again. So we are breaking intermolecular forces. Because notice we're putting energy into the system, but the temperature is not going up. So where is the energy going? It's actually going into breaking those bonds. Very important. Once we're finished vaporizing, and now our substance is a gas, we can now begin increasing the temperature of the gas. And this technically can keep going on and on and on and on. And so this is the general outline of the heating curve. Now, we're not going to only be able to interpret the heating curve, but actually do some calculations with it eventually. Let me show you a little detail that is really interesting. What happens is you can actually heat a substance above its boiling point while it still remains a liquid. So there's usually a little curve that is shown like this in some specific heating curves, and this is called superheating. It's a strange phenomenon, but we'll show you some videos of this. We can actually do some demonstrations as well if you're done. Do it carefully. If you heat, usually you have to have a pure substance. So if there's no impurity in the substance, it's pretty pure. what will happen is you can actually heat it above its boiling point. Usually this is a few degrees, maybe 3, 4, 5 degrees above its boiling point, and it won't boil. It'll remain a liquid, and then it will suddenly boil, and you'll get superheating. You'll get a flash boil, what's called flash boiling. And I will try to remind you of this in class so we can show you some demonstrations of this. But this is actually an interesting little phenomenon that occurs, and that actually is a safety feature in laboratory work. You can accidentally overheat something, and then without you knowing, it kind of explodes, the liquid explodes in your face. This is usually done if you're undergoing something called distillation. Especially applies to the process of distillation, which we'll hopefully be able to do. Alright, that's the heating curve. Now, something very similar is called the cooling curve. It looks essentially the same, except it's flipped. It's a mirror image. And very similar, you begin with the gas up here, and then you cool the gas, and then you get to a flat line. This flat line corresponds to condensation, as you go from a gas to a liquid. Now, the temperature, again, would be the boiling point. Usually we don't call this the condensation point, we call it the boiling point. So that would be the temperature. And in this case, the heat is actually releasing. So in this case, if you were to put heat or energy on the x-axis, energy would actually be decreasing. So energy would be increasing this way, and you know, if you had numbers, you'd see energy decreasing. They put decreasing numbers here. So this would be, in condensation, that would be the energy that's released. Quite a bit of energy is released as bonds are formed. So energy released as bonds form. So now you get to the liquid phase, and you've got the liquid. And the liquid will decrease in temperature as it's being cooled, as energy is being removed, until, again, you get to the flat line. And this flat line represents freezing. And in the process of freezing, again, heat is being released. Now this is really strange, but heat is released. They actually apply this process in keeping fruit from freezing over in the nighttime. So, for example, in places like California or Florida, where they grow strawberries or oranges, what they would do overnight, they would actually sprinkle, you know, the orange on the orange tree. Here's your orange, with water, and kind of spray it with water. And then overnight, what happens as that temperature dips below zero, and usually it just gets cold for a little bit, as that temperature dips below, this water actually freezes on the outside of the orange or a strawberry, and it actually releases heat to the orange, just enough for it not to suffer frostbite overnight, so you can still have produce that's fresh and crunchy. And what happens also, that, you know, little layer of ice protects the orange from further cooling. If it gets quite a bit colder, that can actually protect the orange as well. But that freezing actually releases the heat and kind of keeps the orange warm. Kind of a strange idea, but true. This is actually done with farmers in those areas. So once you're done, once you've frozen the substance completely, it's now solid, you can keep cooling it and get it down to as cold as you would like. Now, just like the heating curve, the cooling curve has a really interesting little phenomenon, and that is actually right below, right here. And this is called supercooling. Just like we saw superheating, this is supercooling. Now this one you can actually demonstrate yourself. What you could do is, if you cool water very slowly, you can do this in the freezer, you can actually get it to remain a liquid below its freezing point. This would be, again, the freezing point of water, or of the substance. And you can actually get it to go down, you know, 3, 4, 5 degrees Celsius even, and it will remain a liquid. And then when agitated, all of a sudden, it jumps up and freezes. It's called supercooling. And what you do is you take out a bottle. You may have seen this, videos of this. You take out a bottle, which is cooled below its, so we'll say this is a bottle of water. It's been cooled below its freezing point, and it could be negative, you know, 3 degrees Celsius or negative 4 degrees Celsius. And just shaking it all of a sudden makes it into a solid. Yeah, it's usually a slushy solid, but it is a solid. It's a neat little effect that we can demonstrate as well. Alright, so that's the outline of the heating curve and the cooling curve. Now let me show you an actual curve that's drawn to scale, and this would be for water. Usually we're going to work a lot with water. Water will be the substance of choice for us as we study this idea of heating and cooling and energy. So this is drawn to scale, which means that the numbers here represent actual measurements. And if you take a look, the boiling point and freezing point of water, here's the boiling point of water, here's the freezing point of water, or the melting point of water. And that corresponds to the first flat line and the second flat line, so these two flat lines. Now what you'll see, first of all, when you draw this to scale, the melting flat line is very short compared to the boiling flat line. This is important. Now ask yourself why this is the case. In terms of when you're melting a substance, you go from a solid. Usually a solid is thought of as ordered arrangement of molecules or particles. And then when you go to a liquid, this is your solid. When you go to a liquid, then they're no longer ordered and they're allowed to move. Now they start to move around. So whereas before these guys were essentially stuck in position, they have vibrational motion. That's all the motion they have. All of a sudden these molecules, water molecules, particles, can now move around. They can slide past each other. So what you've done effectively is, this is a liquid, is you've loosened the bonds. So think of this as loosening bonds. You've loosened these bonds. Now when you become a gas, if you think of a gas, the gas particles are completely free and very chaotic and fly at a very high speed in all opposite directions. And the characteristic here is that there are no bonds between the molecules. So as you go from a liquid to a gas, you've completely broken the bonds. And these bonds are intermolecular forces that are keeping these bonds together. So you've completely broken the bonds. Now ask yourself, does it take more energy to break bonds or just to loosen bonds? It definitely takes more energy to break bonds. So in fact, in the case of water, this right here can actually represent what's called the heat of vaporization that we've talked about earlier. This is heat of vaporization. Now the heat of vaporization is an actual number you can look up, and we'll actually show it to you here in a minute. And this is called the heat of fusion. And the heat of fusion is how much heat it takes to melt a certain amount of a solid. And if you take a look at water's heat of vaporization, heat of fusion, water's heat of fusion is actually about 40 kilojoules per mole. So about 40 kilojoules. And the heat of fusion of water is about 6 kilojoules per mole. Whoops, kilojoules per mole. You'll see these numbers in a little more specific way in a minute. So notice quite a bit more than 6 times, almost 7 times more energy is required to vaporize water than it does to melt water. And you can actually see this on the scale. Here it says that the heat is added toward the bottom, and each division corresponds to 4 kilojoules. So, from here to here, that's 4 kilojoules. And if you take a look, for water, we're roughly going from here, from this spot, roughly to this spot. So we're roughly going to go through 10 of these. 1, 2, 3, 4, 5, 6, 7, 8, 9. And if you add this and this one, that's 10. So we roughly have 10 divisions, which is 40 kilojoules. So water's heat of fusion, or rather vaporization, is 40 kilojoules. And this looks to me like it corresponds to roughly 1.5 of these divisions, which would be about 6 kilojoules. So this is drawn to scale. And again, any heating curve that you see, you'll always see the vaporization line be longer than the fusion line. That will always be the case, no matter what the substance is. Okay? Now, the other thing you can see on here is actually something called specific heat. We also talked about specific heat. The specific heat of water is actually 4.18 joules per gram degrees Celsius. And what this refers to is how much energy it takes to warm water up. And this actually could be related to this line right here, the line that connects the solid and the liquid. So essentially it's the specific heat, it's how much heat it takes to warm up water. And here we're going from 0 Celsius to 100 Celsius. So how much heat does it take to go from 0 to 100? Well, if you calculate it, it looks like it's one division here, and then it looks like it's almost another division. So almost 8. I would say about 7. So this division here is 4, and then up to here would be another 4, so I would say about 7. So this represents about 7, it's getting a little crowded, 7 kilojoules. Now what happens, that 7 kilojoules is divided between 100 degrees of water. Now, usually specific heats, as you'll see, are given in joules, whereas heat of vaporizations are given in kilojoules, because there's so much more, so much bigger. So if I got 7 kilojoules, that's about 7,000 joules of energy. Divided by 100 degrees, if I divide this by 100 degrees, I get myself 70 joules. Now this is actually given on a per mole basis. So what happens is this is for a mole of water. All of this is actually given for a mole of water. 1 mole is the amount. We're usually using a molar amount, so this is 1 mole of water. So if you divide this, if you divide 70 by a mole of water, which is for water 18 grams per mole roughly, if you do 70 divided by 18, do we get there? About 4. About 4, roughly 4. Now the real number is 4.18 if you do it a little more carefully. But you can actually see that you can calculate what's called the specific heat of water from that curve, or from this line. And we'll be able to do this. Okay, this is a bit messy, but realize that this heating curve actually shows us actual numbers. And we're actually going to use these numbers to do some important calculations with water. Let me show you the actual numbers on the next slide, and then in the next video we'll do actual calculations. So these are the specific properties of water. There are 5 numbers here, and corresponding to the 5 portions of the heating curve. So the first one is the specific heat of ice. Now this is how much heat it takes to warm up just ice, solid ice. Now you'll see that this is joules per gram degree Celsius. So this is the specific heat of ice. This will be corresponding to this first portion of the heating curve. And if you have, 10 grams of ice, well, it'll take 2 times 10, 20 joules to warm it up a degree Celsius, and that's what that means. Then you have the molar heat of fusion of ice. This is the number that corresponds to this portion of the heating curve. This is how much heat it takes to melt a mole of ice. So it takes 6 kilojoules to melt a mole of ice. Notice the specific heat is given in joules, the molar heat is given in kilojoules. So it takes quite a bit more heat to melt something than rather just to heat it up. Even though this is on a per mole basis, this is a per gram basis. If you divide this into a per gram basis, it'll still be quite a bit bigger. So, makes sense, hopefully, the molar heat of fusion. And then we go on to the liquid portion. Now we've got liquid water, that corresponds to that portion of the heating curve. 4.18, there's the number. This is actually a very important number. You'll be seeing and using this number a lot in the calculations that are to come. And this is how much heat it takes to warm up 1 gram of water. So if you have 10 grams of water again, and if you want to raise them a degree Celsius, it'll take you about 40 joules. If you have 100 grams of water, or if you have a kilogram of water, well, it'll take up 40 times 100 or times 1,000, 4 kilojoules, something like that. All right, and then the molar heat of vaporization of water, this is that long, flat line that represents vaporization, 40.79 kilojoules. That's the 40 number that I referred to just on the previous slide. And again, it's in kilojoules. This is a pretty big number. It says if you have a mole of water, just 1 mole of water, which is 18 grams of water, not much, and if you want to boil that, you'll better be able to put in a good amount of energy, about 41 kilojoules of energy. This is a good amount of energy. We'll be able to show you how big this energy amount is, but that if somebody gave you this much energy, instantly you would be burnt. You would be very sorry that you asked for it. That's quite a bit of energy. It takes 40.79 kilojoules. So if you have 5 moles of water, you have 200 kilojoules that you'd have to put in. And then after you've done that, the specific heat of steam here is given, 1.89 joules per gram degree Celsius. So this now corresponds to just heating of the vapor, and just keep going up and up and up. Okay, now before we finish, let me just point out, it's interesting that if you take a look, these are the specific heats. So this, and this corresponds to the 3 portions of the heating curve that have the diagonal portions, the 3 diagonal portions. That's where temperature is going up, and you'll see that it has a temperature term in it because temperature is going up in this region. There's a temperature term in all 3 of them. you'll notice that water, the liquid portion, the liquid state, has the highest, about 2 times greater than any of the other two, because you have a lot of motion between water molecules. They can store a lot of heat. That's the idea. The other two numbers you'll notice are kilojoules per mole, and that's referring to the two phase changes. Right, those are the two flat lines. Notice they don't have a temperature term. There is no temperature term. There's no degrees Celsius in here anywhere. That's because you're not increasing the temperature as you heat up, or rather as you boil or as you melt the substance. Okay, enough said. Let's go and wrap this up. We'll do some calculations with the heating curve in the next